Namaskar and hello. Welcome to your favorite Shridevi Classes YouTube channel where we inculcate interest and confidence in science and engineering subjects by clarity of concept and right understanding. Today in our playlist class 12th Physics and Physics Made Easy, we'll discuss few more very important multiple choice question on electrostatics. These questions are related to flux calculation from Gauss law and electric field and potential of spherical charge. Let's start. What is net outward flux from this closed cylindrical surface shown by this brown diagram here in this yellow highlight. Now as per Gauss law, the total flux coming from any closed surface is closed surface integration of electric field intensity over that surface, and it is equal to total amount of charge enclosed within closed surface volume and the permittivity of surrounding media. So in this given figure, this brown closed cylindrical surface enclosed this plus Q charge, this minus Q charge, and there is a line charge density lambda coulomb per meter, and its L length is within cylinder. So only charge which are within cylindrical closed surface contribute flux from this surface, and it is summation of charge, that is plus Q minus Q and lambda L in this L length of cylinder, and that divided by permittivity of this surrounding media is the total amount of flux, option second, from this closed cylindrical surface. If net amount of enclosed charge within this closed surface is positive, then net flux from this closed surface would be also positive and outward, and given by this relation, the flux will be called negative or inward if enclosed charge become in net value negative. So if this minus Q is greater than this plus Q and lambda L, then the flux from this closed surface would become negative and inward. Next question is, what will be the flux through this square plate of size 5 meter by 5 meter from a charge which is placed at 3 meter height from the center of this square plate here? Now Gauss law relate source charge with flux from a surface, but the surface should be a closed surface and charge must be enclosed in the volume surrounded by that closed surface. So using some symmetry of closed surface, we can calculate flux through this square plate. If we assume a cube of 6 meter by 6 meter by 6 meter dimension, and then that Q charge will become at the center of that cube, and in that case the total flux from this cubic closed surface by this enclosed Q charge is Q upon epsilon, and there are symmetrical 6 faces. So from one surface of cube, the net amount of flux will become 1/6 of total flux. Total flux is Q upon epsilon, so 1/6 of that is Q upon 6 epsilon. Now Q upon 6 epsilon flux is coming from 6 meter by 6 meter surface area. Now 5 meter by 5 meter is smaller area, so net amount of flux from 5 by 5 square meter area by this configuration is less than Q upon 6 epsilon. This option 4 would become right choice. In this case, as this Q charge at the center of 6 meter by 6 meter by 6 meter cube contribute total Q upon epsilon flux, and one face of cube will have Q upon 6 epsilon, and 5 by 5 square meter is less than 6 by 6 square meter, so it would have less than Q upon 6 epsilon flux. Two charges of equal magnitude, opposite polarity, closely spaced in a rigid system is called electric dipole, and one such electric dipole is enclosed in a closed spherical surface, and we have to find out a right statement about net flux across this surface, that is psi, and electric field at these points A, B, C here from these four options. As per Gauss law, net flux across any closed surface depends upon total amount of charge enclosed in that surface, and when a dipole is enclosed, the net total charge enclosed in the surface becomes 0. So net flux from this closed surface again become 0. So flux is 0 as in these three options. But significant fact is that in a dipole, electric field exists everywhere in this surrounding vicinity, and there is nowhere at A, B or C electric field intensity is 0. Of course, at perpendicular mid sector or Q axis potential may be 0, but electric field of dipole is depicted here, and force lines come out from positive charge and ends at negative charge, and they make their orientation surrounding this dipole as shown here, and this electric field intensity is given by this mathematical relation, and for any value of theta or non-infinite value of r, there exists electric field intensity which is 2 kp upon r cube on direct axis and kp upon r cube on quadrature axis, but nowhere in near vicinity electric field is 0. So electric field intensity at a point which is on direct axis of dipole, electric field intensity is in dipole moment direction and is equal to 2 kp upon r cube, whereas at quadrature axis point, q axis point, it is kp upon r cube and opposite to direction of dipole moment, and it is also not 0 at b point. In fact, at some position of sphere electric flux is outward and to other position it is inward, and when we take summation, net flux from this closed surface becomes 0 as total enclosed charge within closed surface of this dipole is 0. We have given a closed surface which is passing through observation point A, and there are two charges. One Q1 is enclosed in closed surface and Q2 is outside of it, and we have to find out relation of net flux across this closed surface and electric field intensity at position A in terms of Q1 and Q2. So as per Gauss law, flux from a closed surface depends only on internal charge, and it is internal charge Q1 divided by epsilon as flux from this closed surface, and flux contribution has no relation with external charge, but electric field intensity at this position A will be produced by both Q1 and Q2, and if Q2 is a positive charge, then its electric contribution surrounding it will also be available at position A, and at position A electric field will be produced by both internal charge and external charge, and it is vector summation of two electric field contribution Q1 and Q2 at position A. But for flux calculation, this Q2 charge, if positive, makes some incoming positive flux contribution as well as some outgoing negative flux contribution from this closed surface. So resultant flux across this closed boundary doesn't depend on external charge, and it is solely contributed by internal enclosed charge and is equal to Q1 divided by epsilon here. The total amount of charge on solid conductor sphere of radius r is capital Q, and this charge distribution produce maximum electric field on spherical surface, and that maximum electric field is kq by r square or q upon 4 pi epsilon r square and is capital E. We have to find out electric field intensity at two observation distances, one at r by 2 distance from center and second at 2r distance from center. That means this r by 2 distance position is internal position and 2r is an external position. We know for a conductor sphere all charge will remain only on outer surface, and for spherical charge distribution, charge will uniformly distribute with uniform surface charge density, and there is no internal electric charge. Now electric field is produced by source charges, and since there is no internal electric charge, so there won't be any internal electric field, and anywhere if we construct enclosed surfaces, then since enclosed charge in these surfaces is 0, so net flux across these surfaces becomes 0, and flux is, if the surface is a symmetrical spherical surface, then flux is product of electric field intensity and spherical surface area. Since spherical surface area for this internal Gaussian spherical surface is non-zero, so only thing is internal electric field is 0. So at r by 2 distance, internal electric field is 0 only, and for external observation, the spherical charge act as a point charge acting from center and will have electric field following inverse square relationship, and all distances in this electric field expression are measured from center of sphere, and if distance from center become 2 times spherical radius, electric field intensity become 1/4. So this option 3, internal electric field 0 and at 2r distance external position electric field is 1/4 is the right choice. In the same previous question, total charge on this solid conductor sphere of radius r is capital Q, and on its surface electric potential capital V is given as kq by capital R, where capital R is surface radius. Now for this charge distribution, we have to find out electric potential at a distance r by 4, that is internal position from center, and 4r external position for this spherical charge. So we know a spherical charge act like a at point charge acting from center for all external position and amount of work done in moving a unit positive charge on its surface is surface potential, and it is kq by capital R. And for external position, the same formula works, 1 upon 4 pi epsilon q upon R, where R is distance from center, and if distance of observation position from center is 4r, then potential will become 1/4 of potential on surface. So at 4r, potential is V by 4. So any 2, 3 or 4 could be right choice, and the right choice depends upon potential at internal position. Now at internal position, there is no internal electric field, so no force and no work involvement in movement of charge. So amount of work done up to surface is surface potential, and there is no additional external work required to move charge within sphere. So potential everywhere inside this conductor sphere become identical to surface potential, and this spherical surface behaves like an equipotential surface where potential everywhere at internal position is also potential at surface. So internal potential is capital V, surface value, and external 4r distance potential is 1/4 of surface potential. Option 4 is right choice. This example is conceptually very sound example and very important from examination point of view. We have given two charged conductors pair of radius 3 meter and 4 meter isolated from each other, and they have respectively Q1 and Q2 charge. And if we interconnect these two and no charge transfer will take place from one sphere to another sphere, then what's the correct statement among these four? Now one statement is this wire is too thin to carry charge. That's a wrong statement. If there exists a potential difference, so positive charge will start moving from high potential position to low potential position if we interconnect that by conductor wire. Now here, if charge is not moving from one spherical surface to another spherical surface, it means both sphere got identical potential, and potential on a sphere of radius r and capital Q charge is kq by r. So ratio of charge to radius of both sphere is the same. That's why the potential of 2 is the same. So 4q1 is 3q2 is the right choice. As with this choice, bigger sphere got higher amount of charge and smaller sphere got proportionally small amount of charge, maintain identical potential, and with zero potential difference, there won't be any charge transfer if we interconnect these two spheres by a conductor wire. We have given two hollow spherical surface of radius small r and capital R with common center O, and they have respectively small q and capital Q charge. Now between two spherical surface, there is an observation position at a distance r1 from center, and this r1 is greater than radius of smaller sphere and less than radius of bigger sphere. We have to find out electric field intensity and electric potential at this r1 distance position in this charge distribution of two spherical bodies. Now as per superposition principle, electric field contribution at R1 is vector sum of electric contribution by capital Q charge and small q charge. Now if we consider electric field of this bigger spherical surface, then for all internal positions, electric contribution of charge conductor sphere is 0. So this capital Q won't create any electric field contribution at R1 distance position. So electric field at R1 distance position is only due to small q charge, and for this R1 external position, this small q charge of small r radius behave as a point charge acting from its center, and observation position and center got a distance r1. So this q1 charge at r1 distance produce kq upon r1 square electric field intensity. So either 1 or 3 could be right choice, and that depends upon potential calculation. Similarly, we can apply superposition principle on potential calculation. As per superposition principle, resultant potential at r1 distance position is electric potential contribution of capital Q charge on capital R radius and small q charge on small r radius. Now for this capital Q charge at capital R radius, potential at all internal position is same as potential on surface, and surface potential is kq by capital R. So at r1 distance position, potential of capital Q charge is k capital Q over R, that is on its surface. And for this internal spherical charge, which acts as a point charge acting from center at r1 distance, electric potential is kq by r1, and since electric field is kq by r 1 square, potential is kq by capital R and kq by r1 summation. So this option 3 would become right choice in this example. Two parallel metal plate of area A are charged respectively with plus q and minus q. They have a plate separation small d, and a dielectric media of relative permittivity or dielectric constant epsilon r is placed in between two plates. We have to find out strength of electric field in this dielectric media. So we know a charged infinite plate with surface charge density q upon a sigma produce sigma upon 2 epsilon electric field, and positive charge plate produce radial outward electric field, and this electric field neither diverge or converge and remain constant with distance from charged infinite plate. So here in this dielectric media, positive charge produce its own contribution and negative charge plate also produce its own contribution, and two electric contribution in the same direction get added up, and a resultant electric field become twice of electric field contribution of individual parallel plate sigma upon 2 epsilon, and it become sigma upon epsilon, where sigma is q upon a and electric field is q upon epsilon 0 epsilon r a, as shown by this third choice. We end this learning video with a different type and conceptual question. Potential on the surface of a tiny spherical drop is 60 volt, and if such tiny 27 drops form a big drop, then what is potential on bigger drop? So this potential indicate that drop is charge drop, and let this charge drop got a radius small r, and when n such drops each having spherical volume 4 by 3 pi r cube merge together and form a bigger drop of capital R radius, then volume of capital R radius pair and n drop of smaller radius would be the same, and this relation indicates that radius of bigger drop is cube root of number and radius of smaller tiny drop. Now potential of small tiny drop having charge q and radius small r is kq by r, and it is given small v or 60 volt, and charge remain conserved. So n such small drop each got small q charge when merged together will have total capital Q charge. So on bigger radius with capital Q charge, potential will become capital V. In place of capital Q we can write n times small q, where n is number of tiny drops 27 which are merged to form a bigger drop, and radius of bigger drop given by this relation is cube root of number multiplied by radius of small drop, and k small q over r is potential of small drop. So potential of bigger drop is 2/3 power of number multiplied by potential of small drop, and for 27 cube root is 3 and 2/3 power is 9. So our potential is 9 times 60 or 550 volt in this question. So we have explained 10 different and very important examination question pattern on electrostatics in this learning video. Our other video of same playlist will definitely help you to score high marks in any competitive exam. We end here only with a note of appreciation which you have shown in viewing and promoting our videos. Thank you very much.